June 2, 2025, Mount Etna erupts yet again, but this time something is different. Scientists rush to the scene as the volcano spews a glowing material never recorded in its half-million-year history. If Europe's most active volcano is changing before our eyes, what new dangers and secrets are about to be revealed? Mount Etna rises more than 3,300 meters above the Sicilian landscape, its summit often shrouded in steam and ash. For over 500,000 years, this volcano has shaped the land and lives around it, earning a reputation as Europe's most active and unpredictable volcano. Etna's eruptions are not rare events. Over the past centuries, its slopes have been marked by frequent lava fountains, explosive bursts, and rivers of molten rock that carve new paths through ancient valleys. Records kept by local monasteries and later scientific observatories document hundreds of eruptions, sometimes several in a single year, sometimes separated by quiet decades. What sets Etna apart is not just its size or frequency, but its complexity. Unlike the simple cones of other volcanoes, Etna's summit is a labyrinth of craters and fissures, with new vents opening and old ones collapsing. The mountain's broad flanks are scarred by deep valleys and lava fields, evidence of countless past eruptions and landslides. Each outburst leaves its mark, building new layers and sometimes destroying entire villages. The city of Catania, just 30 kilometers from the summit, has grown in the shadow of this volatile neighbor, its history intertwined with the volcano's moods. Etna's eruptions have long fascinated scientists. The volcano's magma is a blend of deep mantle material and crustal rock, a signature that sets it apart from others in Italy. This unique chemistry fuels a range of eruptive styles, from gentle lava flows that glow at night to violent explosions that send ash clouds high into the sky. The mountain's activity is monitored by a network of sensors, satellites, and field teams, all working to track its ever-changing behavior. For Sicilians, Etna is both a threat and a source of life. Its eruptions have buried fields and homes, but the volcanic soil is rich, supporting vineyards, orchards, and olive groves. Folklore and tradition are steeped in respect for the mountain's power. Over generations, people have learned to watch for warning signs, tremors, gas plumes, the distant roar of an opening vent. Yet, even with centuries of observation, Etna remains unpredictable. Its long record reminds us that, beneath the familiar slopes, powerful forces are always at work, shaping the mountain and the lives around it. June 2, 2025 began as a calm morning on Etna's slopes. By mid-morning, seismic monitors recorded a sharp spike, an unmistakable warning. At 11:20 a.m., the volcano erupted with explosive force. A pyroclastic surge, a fast-moving cloud of ash, rock, and searing gas, shot down the western flank, reaching speeds of 140 kilometers per hour. In less than 60 seconds, the burning avalanche crossed a mile of barren ground, scouring everything in its path. The surge finally halted in Lion Valley, a natural depression that spared the villages below, but not before it left a blackened trail across the landscape. In Biancavilla and Adrano, towns just southwest of the summit, residents described the eruption in vivid detail. Emergency call logs from 11:22 to 11:29 captured the panic. Dozens of calls, voices trembling, some pleading for help, others reporting the sky had turned red and white, flashing like a storm. A local resident, age 70, later wrote in her diary, "I saw the sky turn electric and heard the rumbling. I've lived here 70 years and never felt such danger and relief when it all passed by our town." Tourists on Etna's southern slopes caught the moment on their phones. Videos spread online within minutes, showing a column of ash rising over 6,500 meters, twice the height of the volcano itself. The plume cast a shadow that stretched for kilometers, visible from the coast and even from space. Satellite images later confirmed the eruption's extraordinary scale, capturing a glowing river of material flowing differently than any lava previously seen on Etna. Despite the violence, the surge avoided populated zones. No lives were lost, but the eruption's speed and the appearance of the strange, luminous flow left both residents and scientists stunned. In the hours that followed, Field teams from the National Institute of Geophysics and Volcanology prepared to ascend the mountain, driven by urgent questions about the glowing material and the forces that unleashed it. 12 hours after the eruption, a field technician from the National Institute of Geophysics and Volcanology reached the rim above Lion Valley. The ground was still warm, dotted with blackened debris and streaks of the glowing material that had drawn scientists from across Europe. Wearing full protective gear, the technician moved carefully across the unstable slope, guided by the hum of portable gas detectors and the steady beep of a helmet camera recording every step. Each sample was logged with a unique identification number and precise GPS coordinates, following a strict protocol designed to rule out contamination or mix-up. Chunks of the luminous substance were pried loose with heat-resistant tongs, their surfaces gleaming with a metallic glass sheen even in the midday sun. The technician's field notes describe material unlike any collected on Etna before: dense, glassy, and almost mirror-like, with flashes of deep red and white when turned in the light. Temperature readings hovered above 200 degrees Celsius, forcing a wait before placing fragments into insulated, pre-cleaned containers. Each sample was double-bagged, sealed, and tagged with the time, date, and location. Chain of custody forms documented every handoff, from the crater's edge to the refrigerated transport van waiting below. Within hours, the first batch arrived at the Catania laboratory, still warm to the touch. Technicians logged the specimens into a secure database, then transferred them to refrigeration units to slow any alteration. Photos and high-resolution scans captured their unusual surface textures. Early group chat messages among the scientists reflected a mix of excitement and disbelief. "Never seen this before. Not basalt. Not andesite. What is this?" The strict handling procedures, unique IDs, tamper-evident seals, and dual signatures for every transfer ensured that whatever secrets the material held would be preserved for analysis. The technicians' careful work set the stage for what would become one of the most closely scrutinized volcanic samples in recent memory. At the Catania laboratory, the first analyses produced results that defied expectations. Spectrometers revealed a mineral makeup never cataloged on Mount Etna. The glowing fragments, so striking in the field, showed a blend of iron, titanium, and rare earth elements, but with ratios that did not match any previous Etnian eruption. Thin-section microscopy uncovered crystals locked inside glass, their shapes and zoning patterns more typical of rocks formed far deeper in the earth, well below the known magma chambers beneath the volcano. High-pressure inclusions, stable only at depths where the crust transitions to mantle, pointed to an origin tens of kilometers below the surface. As the samples were distributed to partner labs in Heidelberg and Boston, independent teams confirmed the Catania findings. At the University of Heidelberg, isotopic signatures told a story of mixed origins, mantle-derived material fused with fragments of old subducted crust. MIT's electron microscopes pushed the investigation further, imaging a nanocrystalline texture threaded with platinum group metals, elements rarely found in Etna's typical basalt flows. Some grains even held trapped gases, their ratios suggesting formation under pressures never before measured in this region's volcanic rocks. Amid these discoveries, geodetic teams pored over satellite INSAR and ground-based GNSS data. While routine eruptions can shift Etna's flanks by centimeters over months, this event triggered a sudden, measurable displacement, several centimeters in just hours. The volcano's southeastern side in particular showed rapid movement, enough to prompt urgent recalculations of local hazard models. Scientists debated whether such deep source material and abrupt deformation might signal a new phase of instability. Internal discussions at INGV and Civil Protection grew tense, with some experts recalling the catastrophic flank collapse that sent a tsunami across the Mediterranean thousands of years ago. Despite the mounting data, no clear explanation emerged. The labs agreed. This material was unlike anything previously seen on Etna, and its presence raised urgent questions about what forces were now stirring beneath the volcano. Researchers found themselves confronting not only a scientific puzzle, but a potential hazard whose scope was still unknown. On June 2, 2025, Mount Etna produced a pyroclastic surge clocked at 140 kilometers per hour and a 6,500-meter ash plume, numbers higher than many previous eruptions in its 500,000-year record. For the first time, scientists documented a glowing metallic glass material ejected from the volcano. Early laboratory results confirmed deep origin inclusions and nanocrystalline metals previously unseen in Etna's history. Despite strict field protocols and multi-institution analysis, the full composition and formation process of the material remain unclear. No peer-reviewed hazard models or official civil protection bulletins have yet integrated these findings. As research continues, Etna's June 2025 eruption stands as a reminder: even after centuries of study, Earth's most active volcanoes can still surprise, challenging scientists to revisit what they know and what remains hidden deep below the surface.